An ionic bond is formed when you have a very large electronegativity difference between the two elements that are partaking in the chemical bond. Calcium is a metal, chlorine is a nonmetal, and calcium gives its electrons to chlorine, and this completes the outer shell of actually both sets of ions. At the end of the transfer of the electrons, you have something with a positive charge and you have something with a negative charge. And all of those things are attracted to each other because of Coulomb's law. The force of attraction is electrostatic force. Because of this attraction between the negatively charged cation and the positively charged cation and the negatively charged anion, it reduces the overall potential energy of the system. It's kind of like a ball that rolls down at the bottom of the hill. It's released all of its energy, and it's an exothermic process, which means that when you form ionic bonds, it typically releases energy. There's a bunch of intermediate steps that occur when an ionic bond is formed. We take the metallic element, we get it into the gaseous phase. That requires energy. We can take a diatomic element and we can break that chemical bond. That takes energy. We can take an element in the gaseous phase. We can remove an electron. Ionization energy takes energy. But when we add an electron to chlorine, remember electron affinity is exothermic. And then when two charged particles are attracted to each other, they lower their potential energy. All we care about is this overall difference in energy change, right? All of those intermediate steps really don't matter because we only care about, okay, where did we start and where did we end? And for most ionic compounds, the overall energy change is negative from start to finish. Ionic compounds are organized in a crystal lattice. Not every crystal lattice is a cube. Different crystal lattices can be oriented in hexagons and other geometric shapes, but typically it's an alternating pattern of positive and negative charges that are locked together very tightly because all of those positive and negative charges are stacked together very closely, and since opposites attract, it causes this crystal lattice to be very strong. To break a crystal lattice takes energy. When a crystal lattice is formed with ionic bonds, it releases energy. The lattice energy is the energy required to separate 1 mole of whatever a solid ionic compound is into its gaseous ions. So that's what it's defined as. Coulomb's law comes back into the picture because if we're dealing with different sized ions or different charges, those two things are going to affect the strength of attraction between ions. So for instance, if I'm comparing ions that have the same charges, positive one, negative one, but then if I have bigger ions are going to have greater distance separating them, and therefore their force of attraction is not going to be as strong as smaller ions. The same thing holds true if I'm comparing ions that are similar in size, but I compare their overall magnitude of charge. If I have a +2 and a -2 versus a +1 and a -1, that overall magnitude of charge is going to make the numerator of Coulomb's law much larger. So in general, lattice energy increases when the charge of the ions gets bigger. So if I compare two different compounds, magnesium chloride and magnesium oxide, right? We know that magnesium has a 2 plus, so that's not changing, but chlorine has a -1 charge, oxygen has a -2 charge, and therefore has a higher lattice energy. The other thing we can investigate here is two compounds that have similar charges but different sized ions. So you can see here, sodium bromide has a lattice energy of 732 kilojoules per mole. Sodium iodide, we're talking about similar charges, right? +1, +1, -1, -1. But iodine, the iodide ion, is a little bit bigger, which causes the force of attraction to actually go down. So those are the two trends that I notice, and there are some deviations from this rule. We're not going to get into those deviations right now. There's also a simulation that I'm going to post on Canvas for you to use in order to evaluate Coulomb's law and see how the forces of attraction of two charged particles differ with charge and size. Let's go through some practice problems, and I'd like you to look at these situations and be able to apply Coulomb's law to explain your observations. So pause the video and see if you can go through these problems. For the first question, I'm comparing sodium chloride and potassium chloride. Well, these two ionic compounds have identical charges, right? +1, -1, +1, -1. However, sodium 1 plus only has 2 energy levels of electrons. Its atomic radius is smaller, which therefore is going to increase the lattice energy and make it have a stronger force of attraction in its crystal lattice. When we compare magnesium oxide to magnesium chloride, magnesium oxide has O2 minus, which has a higher charge compared to chlorine 1 minus. In addition, we know that oxygen has a smaller radius, so there's less distance between it and magnesium. So there's two different ways to justify why magnesium oxide would be expected to have the higher melting point. When we look at the ability of a substance to dissolve in water, water is polar, and it has the ability to disrupt a crystal lattice. It would make sense that aluminum oxide has a harder time dissolving in water. Water has a hard time taking the crystal lattice apart because aluminum has a +3 charge compared to the +1 charge of sodium, and therefore I would expect that when aluminum is ionically bound to oxygen, it would have a greater force of attraction because of the greater magnitude of its charge. A quick review of metallic bonding. The image that you should have in your head of what a metallic substance is, it's organized in a crystal lattice. Typically, metals have very high melting points, but not quite as high as ionic compounds. We say that the electrons are delocalized. What does that mean? It means that the electrons are free to move within the crystal lattice, and no one atom really possesses those electrons at any given time. We can use this to explain the fact that atoms have the ability in this sea of electrons to roll, to tumble, to move past one another, and that's what makes metallic elements so malleable. But this sea of electrons is also a pretty strong attraction, so it bends but it doesn't break. So that's why metals typically have very high melting points. We also know that metals are very good at conducting electricity because electrons can travel through the sea of electrons very well. And the vibrations from heat energy can be transferred by these atoms because they have a very high degree of movement within that sea of electrons. In metallic bonds, the metals pass their electrons to each other because the metal atoms have very low electronegativities and aren't really attracted to the electrons in the first place. They form large groups of delocalized electrons in a crystal lattice compared to other structures of other groups of elements. Alloys are specific types of metallic substances in which you have an elemental metal that has been mixed with at least one other element. The addition of an extra element can change the overall properties of that metal. For instance, we can strengthen steel by adding some nickel and some chromium to resist corrosion. We can also change the overall appearance. We can strengthen the metal, or we can make it cheaper. There are two types of alloys that we can form. A substitutional alloy takes metal atoms that are similar in atomic radius and simply substitutes their spots within the crystal lattice. So 14 karat gold. Good example of that because silver and gold have similar atomic radii. A substitutional alloy doesn't strengthen the metal nearly as much as an interstitial alloy. An interstitial alloy takes an element that is incredibly smaller than another metallic element in the alloy. So steel is an example of this. The carbon atoms are able to wedge themselves within the tiny gaps of the crystal lattice. And kind of like different size stones, like if you have a stone path, you'll see different sizes of rocks because the larger rocks can't move around if there's smaller ones that are wedged in between the tiny spaces. An interstitial alloy actually increases the rigidity much more. So that's why steel is a lot stronger than something that is a substitutional alloy. We finished our introduction to ionic and metallic bonding, and we're going to move forward with some properties of covalent bonds in our next mini lecture.